What is that distributed algorithm? First, let's capture two shorthand notation. Okay, one is if you sum up those sources whose rates from those sources that belong to the set of sources using link L, we call this Y sub L, the load on link L. It's just shorthand notation of summing the rates from the right sources. We can also give a mirror image of what happens on a link. Okay? On a link, we're going to see that there is a pricing signal. The physical manifestation turns out can be packet loss or packet delay. And the mathematical interpretation is the Lagrange dual variables. So this is the physical manifestation, this is the mathematical representation. Okay? And on each link there is such a pricing signal P that's going to be fed back from the network to the sources to enable the negative feedback loop. And we're going to sum up all those from the links that's along the path used by source I. Keep writing as source I as given by this routing. Okay. So by summing up all these PL with respect to the path of a particular source I, we get a number, call that QI, because we're talking about a particular source I. This is the path price, because it's a sum of the prices. Again, it's an interpretation, as mentioned at the beginning of the lecture, along the path used by source I. And this YL is the shorthand notation for link load. Okay? It is the sum of the load from the sources that's using this link. Because routing is fixed and given, we don't get to change the summation index. Okay? But we get to change X, and we'll be varying P in a dynamic way. So just remember shorthand notation, Y sub L, link load, Q sub I, path price. Skipping the very interesting derivation, here's what we end up with. Okay? Each source I will autonomously run the following update iteratively from discrete time slot t to t plus 1. You're going to update your rate, okay, x at time t, basically as the demand function, where the price is the path price at this time t, and the path price at time t will be the update from the path price from the last iteration t minus 1. That will be down here in a minute. Okay. So this says that if you are source I, just look at your total path price, and that is the price you have to pay, and put it into your demand function. That should be your source rate. Now what is demand function again? You may remember it is the utility function's first derivative inverse. Why is that? Because demand function is derived by looking at the net utility maximization. Look at my utility minus the price I have to pay, which is the path price for the path I'm traversing, times the volume, which is X. You maximize this over X. Then you will see that X as a function of price is U prime inverse. Okay? And that is the demand function. Exactly as what we saw back in lecture 11. So this is done at each time slot t at each source I. And each link L will also autonomously execute the following computation. E will update the link price at time t from the link price in the last iteration t minus 1 by updating it with the following summation. You look at the YL at time t now, the link load at this point, and the supply. This is demand, this is supply. Supply is fixed, because we assume the fixed capacities on each link L. Demand is dynamically changing based on the price that you have been generating. And the difference is the difference between demand and supply on your link. And this is the direction of change. Does it make sense? Yes, it does. If the demand is bigger than the supply during this step of the transient, then you're going to increase your price next time. When this P is increased, then all those Qs, okay, for those sources who use this link L will see a bigger Q. As Q becomes bigger, U prime inverse of the demand function is a decreasing function that will make the source rate lower. Exactly what happens in many marketplaces in an iterative way. When demand exceeds supply, you say rank up the price. If the price is cranked up, then the demand will drop. So in the next iteration, those sources using link L will see a smaller x, and therefore their total sum y, the link load, will be smaller. That's moving in the right direction. When y is bigger than c, this iteration, next iteration will be smaller. Conversely, if the current demand is actually less than the capacity, then, well, you're not fully utilizing this link's capacity. So you're going to see a smaller P, and that will reflect in smaller Q, which will reflect into a bigger X, and then reflect in a bigger Y. Next iteration, demand will go up. This is a very smart and intuitive arrangement. So this direction is correct. We just need two more modifications. Number one is, while the direction is right, we need a little thing called the step size, denoted by beta here. Beta is some positive constant. It's called step size because it says even you've got the right direction, you don't want to overshoot. Okay? To those of you who have played golf, not me, but played golf on Wii, which is very difficult, you know that when you get close enough to, here's your ball, okay, here's the hole, to the hole, even if you get the right direction and you give too big of a kick, okay, the force is too big, you'll overshoot and land over there. Then you say, all right, the right direction is this way, right direction, but you overshoot again. And this may oscillate back and forth unless you start to kick with smaller forces as you get closer and closer to the hole. So that force to use to hit the golf ball is the step size. You don't want to oscillate and overshoot back and forth, so you want to use a smart step size rule. One rule says that if the step size is a constant, independent of iteration t, and very small, then when it's sufficiently small, then you can guarantee convergence, meaning you will hit it into the hole. Another rule says if I make B smaller and smaller as I move along the time axis, okay, as I get closer and closer to the hole, I start to be more and more careful. That can also guarantee convergence. So the selection of the step size in a distributed or centralized way is both a science and an art. We just don't have time to talk too much about it. A little bit more in advanced material. But for our problem, there are simple and good choices of beta. Simple in the sense it's easy to come up with it, and good in the sense it will guarantee convergence. The second modification we need is that these prices, okay, cannot be negative. Okay. So you're going to say if it becomes negative, we'll just take it as 0. We usually use the symbol a big bracket soup plus to denote the fact that if whatever's in the big bracket dips below 0, we just take the 0 as the floor. All right, now this is our algorithm. Okay, at each source I, you just look at your current path price into your demand function driven by your own utility function, and at each link L, there is this price update. And as t goes on through the iterations, you actually guaranteed, as long as the step size is smart enough, to converge. And converge to what? To an optimizer of this convex decomposable optimization problem called the basic network utility maximization. The proof of that is in advanced material. Here we just want to look at this and make sure we can intuitively understand why it makes sense. Number one is that we know the direction is right. Bigger demand will lead to smaller demand next time. Smaller demand now lead to a bigger demand next time with respect to a given fixed link capacity. Number two, is it distributed? Well, it is actually very distributed. Now, the source rate updates are very distributed. All you need to know is, as a source I, your own path price, Qi. Not only you don't need to know the other sources. So you are source 1, you don't need to know Q2, Q3, and so on. In fact, you don't even need to know the individual link prices along the links used by yourself. You only need to know the end-to-end path price. The link price update computation is also distributed. You only need to know the load on yourself. Say you are link 1, Y1. You do not need to know Y2, Y3, what happens on the other links. And you don't even need to know the ingredients in your Y1. You don't need to know the individual source rates. You just need to know the total link load, the sum of the source rates among the sources using you. So this is a very distributed action. As long as the sources can get these path price with some message passing, okay, either explicit or implicit. As we'll see in a minute, actually in the next module, I guess, we'll see that it can be done in an implicit message passing to get these path prices interpretable as the end-to-end loss rate or queuing delay. Number 3, there is a very nice economic interpretation. Just like back in lecture 11 when we used the pricing to coordinate demand and supply. Back in lecture 2 when we used pricing to coordinate demand and supply in auctions. Okay, now we're using pricing, at least as interpretation of this machine protocol called TCP congestion control. Prices again coordinate demand and supply in a very fast time scale around round-trip time scale, and in this case distributedly over a network. We're looking at a more complicated version than the simpler ones before. Now we have to run it over a network, and the good news is that it can be done distributively. And this can be summarized in a feedback loop. This is the negative feedback loop that we were looking for about 1 hour ago at the beginning of this lecture. Okay. Each source labeled by 1, 2, 3, I draw this way because I want to highlight the fact that their actions will be autonomous. It's distributed. Actions will decide an xi. This induces a vector x into the network. Okay, you can represent as this routing matrix R. Then each link only sees the link load y's. Again, autonomous action distributed across the links. And then they will update these prices PL independent of each other through the network, and the sources will only see the corresponding path prices QIs. Okay. X goes up, P will go up. Q will go up, then X will go down, then Y will go down. And with a sufficiently smart step size beta, this is guaranteed to converge. Now, will they converge using existing TCP protocols? We'll come back to that towards the end of the lecture. But first, let's look at a small numerical example using the same topology that we saw